If we can toss coins, can we also roll dice using a computer? The answer is yes, and we'll do that by generating categorical random numbers. A categorical random number takes integer values between 1 and k with probability pk. These probabilities are real values between 0 and 1 that add up to 1. To generate samples on the categorical distribution, we're going to use a similar strategy to the Bernoulli distribution. That is, we're going to divide the 0-1 interval into subintervals. Each of these subintervals is going to be assigned to one of the possible results of the categorical random number. So for instance, here we have divided the interval 0-1 into 6 subintervals of equal length, and that corresponds to a die, to rolling a die. So here we would have phase 1, phase 2, phase 3, phase 4, phase 5 and 6 of the roll of a die. We're going to sample uniformly between 0 and 1. And for instance, if the sample falls here, we would get a 5. And if it falls here, we would get a 2. Since the length of the subinterval is equal to the probability of that particular value, that will give us categorical random numbers with the specified probabilities. The pseudocode is as follows. To generate xi from a categorical distribution with the vector of probabilities p, this is a vector that collects the value of pk, and we can take k values. We're going to sample from a uniform 0-1 distribution and then determine whether this sample falls between the left limit and the right limit that define the subinterval associated to that particular value of xi. In this demo, we're going to generate random numbers from a categorical distribution. The parameter for the categorical distribution is a vector of probabilities. A vector of probabilities is composed of real numbers, each of which is between 0 and 1, and whose sum is equal to 1. Here, we're trying to represent an experiment in which we're rolling a die repeated times. Therefore, it is a vector with 6 components, each of which corresponds to one of the faces of the die. So for instance, the face corresponding to value 1 has probability 1/6, the face corresponding to value 2 has probability 1/6, and so on until the face that has the value 6. So the number of possible outcomes is simply the length of this probability vector. To sample from this categorical distribution, first we take this probability vector and calculate this cumulative sum. Basically, this is a vector that has the first value 0, the second value 1/6, the third value, the sum of the probabilities of the first two outcomes, so in this case is 2/6, 3/6, 4/6, and so on until 1. Then we generate a uniform 0-1 random number, in this case 0.4, close to 0.4. And then we compare this random number with the values of the vector QP. We count how many values of this vector are below u. In this case, there are 3 values. Well, that's the value that we're going to assign to xi, which is the random variable that follows the categorical distribution. If instead of a single random number, we simulate a matrix of m rows and n columns of random numbers from a categorical distribution, we can actually compare the empirical frequency of values realized and the theoretical probabilities that we have specified in the random vector. So here's the comparison between the theoretical probabilities, which are in red, corresponding to each of the 6 phases of the die, and the empirical realization. So in blue we have the frequency of values that we have empirically produced. And we see that they're close to each other except for sampling fluctuations.